Good evening and welcome all to the GEMA webinar on corn oil, the next revenue stream for India's ethanol market. It is my immense pleasure to welcome Mr. Chris Clausen, our today's webinar presenter and speaker. Mr. Chris Clausen is the Director of Technology at Trucent Separation Technologies, a leader in advanced separation and fluid solutions for the industrial and bioprocess industries. Since joining Trucent in 2016, Chris has led product development and engineering initiatives, particularly in corn oil extraction technologies that help ethanol producers maximize yield and process efficiency. A graduate of the United States Merchant Marine Academy, Chris previously served as an engineering officer in the US Navy and Merchant Marines, gaining extensive experience in fluid separation systems. Today, he oversees technology development, engineering, fabrication, and field implementation across Trucent's product portfolio, while driving innovation for the ethanol, food, beverage, and bioprocess sector. I once again welcome Mr. Chris. And please take over the session. Thank you.
Thank you, Nitin. And thank you all for joining. I appreciate the opportunity to speak with you. As Nitin mentioned, I'm with Trucent. We were established in 1997, and we were among the first to extract corn oil in 2008. We continue to be a leader in corn oil extraction, and our team is very excited to bring our experience to the Indian ethanol market. It was very important for our team to build systems in India for India. And to do that, we've trained engineers and technicians to be able to support the region and the systems that we're building in India. Mr. Ramesh is with us today. He's with our channel partner, Crab and Tower. And I'm excited to talk about corn oil with you today. I figured we'd start at the very beginning, the corn kernel. The endosperm makes up about 82%, and where the starch and protein reside. We're going to be focusing today on the germ, where there's 3 to 4% oil that we're going to be trying to capture and extract. I want to start with what distinguishing a little bit between distiller's corn oil, which is what we're talking about, and the term that is generally used for oil coming out of a corn ethanol plant versus food grade corn oil. These are two different things. I'm not aware of any country that has approved distiller's corn oil for human consumption, but it is a very high value product for several other industries. It is a very high quality fat source for the animal feed industry, and where we're seeing a tremendous amount of growth for demand for corn oil is in the renewable fuels sectors. Because of its low carbon intensity score, it makes it a very sought after feedstock for renewable diesel, biodiesel, and sustainable aviation fuels. It is the fuel mandates, the green fuel mandates across the globe are driving up demand for corn oil. So it is also there's also a large export demand that is available to any DCO producer. Looking into the future and future revenues, future demand. Right now, demand is strong, but it's only expected to increase pretty dramatically over the next several decades. That growth is mainly being fueled by the global green fuel mandates that I mentioned. India has some pretty strong fuel mandates. The biodiesel blending program is expected to hit 5% blend by 2030. And that's going to require quite a lot of feedstock to be able to hit that mandate. The chart here on the left shows the three co-products out of a corn ethanol facility, both in U.S. dollars. So in any country, anywhere where DCO is extracted, it is the highest value co-product on a mass basis. You can see that in U.S. dollars and rupees. These aren't conversions from dollars to rupees. These are current market conditions. As the demand for biodiesel and renewable diesel and SAF continues to increase in India, we expect the price for corn oil to also increase. That's what's driving the U.S. market right now to such great price. So now that we're excited to extract corn oil, the question is, how much can we get? I put this slide together to give you an opportunity to do a rough estimate of what you could expect from revenues or from yield, industry averages, and then we normalize those to kilograms of oil per 1 ton of corn. The corn oil separation is a technically difficult one. There are a lot of variables that affect not only yield, but oil quality. Over the last 18 years, Trucent has studied over 100 variables that affect yield and quality. These are just a few. The metric that was on the previous slide is a common one. It's either kilograms per ton of ground corn or pounds of oil per bushel of corn here in the United States. That metric is affected by all of these variables. And so a more accurate metric that we like using is percent capture of free oil. What we're able to capture, to extract, is the free oil available where the extraction is happening. So you take what is available at that point versus what is captured. The physics around how we extract corn oil or any separation, fluid separation, is governed by the physical law of Stokes' law, which is what you see here. And what this is telling us, so this is a bit of a modified version of Stokes' law that is used for an oil extraction. What this is saying is that the velocity at which the separation happens is dependent on the droplet size squared times the difference in densities between the fluids times the centrifugal acceleration over a constant times viscosity. And that is how we extract corn oil. That centrifugal acceleration represents us engineering gravity, and we do that with centrifuges. There are two basic types of centrifuges from a high level that are used in this application, and that's the vertical distack centrifuge and the solid horizontal bowl centrifuge. It's important to note that any centrifuge being used in this application needs to be designed for corn oil extraction. There are hundreds or thousands of different centrifuge designs, both vertical and horizontal. But there are so many design variables in a centrifuge that to be successful, you really need to start with a design that is meant for an oil extraction. Just because it spins doesn't mean that it's going to separate the corn oil. Like I said, the corn oil separation is actually quite a difficult and technical one. So starting out with a design that is going to be successful is very important. Looking into these two different types of centrifuges, we'll start with the horizontal type. Um, the uh, the horizontal bowl is rotating, um, and within that bowl there's a scroll with corkscrew flights attached to it. The bowl and the scroll both rotate, but at a different speed. So there's a delta in the speed between the two, uh, and uh, and that's important in its operation. And we're going to walk through that now. Um, the feed or the syrup, the thick slope, is injected through the center of the scroll and put into the bowl. It gets up to rotational speed. The delta between the bowl and the scroll allow the flights to move the solids to one end of the bowl. The end of the bowl that has a taper to it allows the solids to compact. Just generally, the term used is to create a beach of solids, which forces it then out one end of the bowl. That allows the liquid phases to move to the other end of the bowl. As the liquids rotate within the bowl, there's a phase separation. The corn oil creates a light phase at the inner diameter of the bowl, and the de-oiled syrup, being more dense, creates a layer at the extremity of the bowl. All three phases are overflow the bowl and are gravity fed to tanks below. These are elevated systems because they don't have a means to generate pressure to move the fluids. So they're raised up off the ground or the deck in order to allow space for capture and then transfer from below the centrifuge itself. These are larger centrifuges. Because of their size, they're limited on the rotational speed that they can operate at, which has its pros and cons, which we'll get to in a moment. But they're able to generate G forces that allow it to separate down to the 20 to 50 micron uh, uh, particle size range. The vertical distack centrifuge is a smaller system, more compact. There's a rotating bowl within a housing similar to the horizontal, and also similar to the horizontal, the feed goes down the center of the bowl. In this instance, instead of having a constant solids discharge, the solids are built up in the bowl and then periodically discharged, generally called a chute because it's quite there's a loud noise that comes with that as those solids are expelled. The liquid phases then travel into the distack where it gets its name. The distack is just a set of plates essentially, and that increases the relative surface area within the bowl so that the phase change can happen in a smaller area, which just increases efficiencies. So these bowls, because they're not don't have the mass of the larger horizontals, and the way that they're manufactured, are able to spin at higher RPMs and generate more G-force. That higher G-force and increased relative surface area allow these systems, generally speaking, to be more efficient and to separate down to a finer micron. The Across the industry, the higher performing systems can separate down to about a half a micron. Um, Similar to the horizontal, you get a liquid phase separation in these bowls. So your solids build up on the outside of the outer diameter within the bowl and are periodically discharged. The two liquid phases separate within the distack. The oil phase is routed to a centripetal pump, and which creates pressure, which can then actually be pumped downstream. Similarly, the heavy phase or the de-oiled syrup is sent to a centripetal pump, and centripetal, not centrifugal, because the fluid is already spinning. We don't need to spin the centrifugal vane. So we use the motion of the fluid to create that pressure, and we're able to discharge these liquid phases under pressure, which allows the skids to be a little more compact, or the systems to be more compact, and not have the need to be on a raised platform. Like I said, there are advantages and disadvantages to either of these technologies, with proper design, engineering, and the auxiliaries that are needed for each of them. Both are very successful in extracting corn oil. Uh, Both, I would say, or any corn oil extraction system, it is very important to maintain a regular sampling regimen and testing regimen in your lab. And we'll get into that in a little bit, or part of that in a little bit. But being able to make real-time changes to either of these will keep them running at high efficiencies. The horizontal systems, because of how they're manufactured, and their general design, where they don't have as tight of tolerance on or gaps, make them more robust to handling feed variations, higher solids percentages, changes in viscosities or solids loading. And because of that, they have a lower risk of plugging. Plugging is a term of when the solids get so compacted that they no longer flow through one of the centrifuges. Um, but they're limited on G-force and efficiency, and they're also larger systems, physically larger systems. The vertical disc stacks have better efficiency and can generally produce a higher quality oil. Uh, and because of the higher tolerances, have generally less major component wear, but they do prefer a more steady feed to the centrifuge. So making slower changes to the feed makeup is beneficial for this type. In the market today in India, both options are available. In many instances, they're coming just as the centrifuge itself. And that's important to note because it's going to be on the plant to engineer the auxiliary systems, the safety systems, the handling systems, that will make the recovery or the extraction successful. Those auxiliary systems are vital for the success. Over the last 18 years, Trucent has developed a turnkey system, that is a skidded system that includes all the auxiliaries and controls that are needed, everything from automated cleaning and process operation to the safety controls. They also come with our proprietary corn oil conditioning system. This is a system where you send the raw oil to. No centrifuge is perfect all the time, especially as there are fluctuations in the feedstock. What our conditioning system does is it takes that raw oil and allows the operator to control a steady and finished oil product, where you can maintain a set purity level, moisture level, so that you have a constant product within the moisture and suspended solids or insolubles levels for whatever spec you're trying to meet. Along with the technical system, as I said, we've trained a team and built capacity in India to be able to support the systems. We like to say that we're there for you from harvest to harvest and anything that may happen in between. and the expertise of how to optimize and get the most corn oil out of the system uh, that we've installed. So now that we've covered the how, I want to touch just on a few of the variables that are important to know about that you can control to be able to get as much oil as possible and really optimize any extraction system. So as most things go, we go back to the root, which is the physics. The When you're looking at Stokes' law, there are a few variables that we can control and some that we can't. The densities are fixed and defined. The centrifugal force is a design variable of the centrifuge. So once you've landed on a system that you're going to install and implement, that's going to be a fixed variable. But we can control droplet size, viscosity, or we can influence. I shouldn't say control. We can influence droplet size, viscosity. And I threw in another variable, which is the time exposed to gravity. There's a unit that we use called G seconds, and you can influence that by the flow rate to the system. Obviously, a lower flow rate into the centrifuge will mean more time within the bowl. So the syrup is exposed to more G seconds, how much gravity over how much time. We're going to start with droplet size. If you're looking at the math, you'll see that the droplet size, or D, is squared, which means if we double the diameter of an oil droplet, we'll quadruple the velocity at which it separates, or increase, quadruple the efficiency at which it is coming out. We do this in a few ways, increasing the droplet size. There are a family of chemicals that are available that will create larger droplets. They're commonly known as deemulsifiers. Although they do have a deemulsifying component with their the way I like to think about them is as conglomerators and coalescers. So if you picture a octopus with long tentacles, what the chemical is doing is becoming a barrier between a negative charge that's hold the droplets together. So I like to envision the octopus being able to reach its tentacles out and grab the small droplets, bringing them to a nucleate and create that bigger droplet. In order to do that, you have to have the correct dosage, contact time. Heating helps. The hotter the syrup, generally the better or the more efficient the chemical can react or coalesce those droplets together. The sweet spot, if you will, is 90 degrees Celsius, but it certainly doesn't need to be that hot. There are systems that allow the operator to have more control over what is going to the centrifuge, and it's really just a feed tank. They're called heat and hold tanks, feed tanks. But it's just a wide spot in the system in order to give the chemistry more time to create those larger droplets. I will mention one caution that if your system does include a heat and hold tank, it's important to have a gentle recirculation or agitation. Recirculation is generally a more efficient way to keep the oil in suspension in general suspension so that it can be extracted. But if you're watching your oil yield trend and you see a drop off in oil production without any other explanation, if you take a look inside that tank, you may see oil stratifying at the top of it. which just means it needs a little more agitation to keep it in suspension so that it can be sent to the centrifuge. In order to know the proper dosage ratio, heat and hold time, everything goes back to doing benchtop sampling. That knowing what is going on, going to the centrifuge, what is going on in the centrifuge is very important to maintain the highest efficiencies. So taking samples and doing a microscope analysis. Um, so on this slide, if you look on the left, you can see the small oil droplets in the feed. And on the right, after it has been dosed with chemical, you see these much larger oil droplets that are a lot easier to extract. You'll also see that in a benchtop centrifuge test. So you take a small sample, spin it on a benchtop, and you'll see the break. You'll generally see 3 or 4 phases, and a solids phase, a de-oiled syrup phase. There may be an emulsion phase, and then your oil phase. So you want to do testing at different dosage ratios, ppms, um, for your current conditions. When you do that, you can test at 1, 2, 3, 400 ppm and see which has your best oil break. On the right here, you'll see 2 photos. The left photo is before a dosage correction or adjustment. So you can see a small oil layer, but then a really large emulsion area. If you, then make an adjustment and resample, you see that oil can be made free, and that's what we're looking for. Any centrifuge extraction system. And so by testing, we're able to see what conditions we can create to allow the most free corn oil to be available to it. Same thing goes for hold time. If you've got that option and heat, you can test at different hold times, different temperatures, and different dosing ratios. I say ratio, and it's an important distinction between ratio and rate. Dosing to ppm is more efficient and consistent than dosing to rate or milliliters a minute. So focusing on the ratio, the ppm, will give you higher performance over time. Where you decide to inject the emulsifier is also important, especially if you don't have a hold tank. Giving it as much time as possible to have contact with the oil droplets, and then making sure that it is as well mixed as possible, using a dosing quill to get the demulsifier into the center of the pipe, or by injecting at the inlet of a pump will allow the pump to do the mixing. A dosage quill will prevent, if you're just dosing into a pipe, the top of a pipe, you're going to have some contact, but a lot of that demulsifier is just going to run along the pipe and not be mixed into the syrup in order to have contact with the oil. The other variable that I want to touch on is viscosity. Viscosity has a tremendous impact on the effectiveness of an extraction. If you think of trying to remove a marble from peanut butter, if you heat that peanut butter up and make it less viscous, it separates a lot easier. It's really the same concept here. In a lot of instances, customers will only be looking at solids content by percent weight. Solids content is a factor of viscosity, and just the percent weight really won't tell you the whole story. If you look at these photos, you can see several different solids breaks. There, in the fourth one here, there really isn't a discernible solids break, but a very nice, healthy free oil break. And that sample may be less viscous than a sample like we have in the second one, where there's very low solids or a nice break, but we still have this big emulsion section, uh, and that may be due to the viscosity of the syrup. And that could be because of a number of things. The enzyme package that's used, anything from fermentation, the heat history on that the oil experiences is a contributor as well, through distillation and evaporation. Depending on what is happening prior to the oil separation or the oil extraction, makes an influence on the viscosity. Um, Having a complete and high quality fermentation is also important. If you have incomplete fermentation or high starches, high sugars, those will absolutely contribute to a more difficult oil separation. In a lot of cases, when you have upsets like that, it's best to bypass the corn oil extraction systems, so that the solids loading going to them, or burnt sugars, things like that, don't affect the centrifuge, because those can have a very negative impact. Other ways to help influence lower viscosity are the demulsifier aids. Those can be more efficient at lower viscosities. A finer grind not only helps other areas of the ethanol process, but uh, certainly allows for a better oil separation or extraction, and heat. The hotter you heat syrup, the less viscous it's going to become. Um, and then, as we touched on, the nature of the solids, having compact solids versus more fluffy solids, and that's where looking at the upstream is important, and making sure that your dosage ratio for your demulsifier uh, is important. I appreciate your time. I want to give enough time to be able to answer some questions, um, and I hope that everyone is excited about corn oil. We think that it's going to be a major part of the Indian ethanol market's future.
Thank you, Chris. My fellow participants, uh, you can ask the questions from the Chris, and he will be giving you the sufficient replies for the same, please. Thank you.
Good evening. My name is Ajay Kapoor. Actually, I have a query, related to corn oil. What the benefit we will get in the corn oil? Can it be compensated with the reduced prices of DDGS?
Great question. So in other markets, what we've seen is obviously there is a decrease in fat content in the DDGS. Uh, in the early years of corn oil extraction, it was obviously a hot topic of conversation. What we've seen is that the, the market price ends up being the market price. There are some ethanol plants that control or have a higher fat content in their DDGS, but overall, uh, the benefit of the revenue of corn oil has driven the market to accept a lower fat content in DDGS. There hasn't been in any of the markets that I'm aware of a negative reaction to the price, at least in my experience, that the DDGS are still very valuable, still have a need and an outlet. It's just that by extracting the oil, not only is the financial benefit for the producer higher, but the value of the DDGS is still high enough to really keep stable commodity prices on the DDGS as well.
So do we have any cost benefit analysis sheet or something like that, which can give the real reflection? What type of benefit we can expect out of it? Means the
Yeah,
ROI, if we are
absolutely.
going to,
Sorry, go ahead.
sorry? Yeah, if you are going to put the plant, this one, corn oil extraction plant, so what will be the actual benefit and what will be the ROI of it?
Yeah, absolutely. We can help with that. If you reach out to Mr. Umesh, we can do a case study on your specific plant. You can also run a revenue calculation on the with the information on that previous slide. But we can absolutely help with that. If you reach out to myself or Mr. Umesh, we can do a case study for your particular plant.
Yes, sir. Sure. You can reach out to me, sir. My email ID is there in the chat box, and you can write to me. I will try to support you.
Okay, sure. And third question is in terms
Sir, your voice
of,
is not too audible, sir. Can you repeat?
some people are taking DDGs for the special, in terms of to get the better. Asking, I'm just asking, it is going to the solvent extraction system. So which one is better in terms of the corn oil recovery? Is it solvent extraction or if we will do mechanically?
By far, the market has shown that a physical separation is more cost effective, safer, and that is how the corn oil is extracted across North America, South America. I know of solvent extractions, but they're very few and far between, and generally because of a very specific reason where the product is going. The CapEx, OpEx, safety has driven all the markets that I'm aware of to a physical separation. Yeah.
Okay.
I hope that answers that.
Okay, and the one more query, related to when we are saying, can we, you told us, that it goes into the biodiesel and all that.
Yeah.
Can we convert this into the edible oil also?
Into renewable diesel?
No, I'm talking about the oil which we are, recovering this. What are the impurities, which restrict us to convert this into the edible oil? Or how can we make this as a edible oil?
As edible oil?
Yeah, edible oil, edible corn oil. Can it go into the edible oil or no?
I'm not aware of any food safety regulation that has allowed distillers corn oil into an edible market. It is the main distinguishing market factor for distillers corn oil versus food grade extracted oil. So I'm not aware of any country that has certified
No. My
this
my
oil as
question was my question was what are the impurities in it so it cannot be used as a edible oil? What are the impurities? Can we remove that? Or do we have any technology to make this oil as a edible oil
I'm not
to get
aware of
the
any, but I can talk with some government regulators and our science and lab team. And I can follow up with you on an answer of what drives it to be non-edible, not non-edible for human consumption. It
Yeah.
is grass are generally accepted as safe for non-human consumption. One of the large outlets for corn oil is the animal feed market. It's a very high fat, high quality fat that is used as a supplement or an addition to animal feeds. But I would need to dig a little deeper and follow up with you on what exact properties of it has led governments to not consider it safe for human consumption.
Okay. Thank
And
you.
it's important to note the additives that we were talking about, a lot of those are food grade. But just because that additive it doesn't make the oil itself appropriate for human consumption. But I can follow up
Because
with you if you can reach
because my
out
you
to.
know my query was because can we make more value add out of it? That's why I'm asking what was the what is the impurity? That's why our environmentalist or government is not allowing to go into the edible oil. So that I want to understand, and what technology we should go for just to remove that impurities to make it edible oil.
Like I said, I'm not aware of any global market or country that has turned that has a system that will allow distillers corn oil to become a human grade food safe. But there are impurities in it that we are aware of that we can remove to give it a higher value. When taking any feedstock and turning it into renewable diesel or sustainable aviation fuel, there are impurities that in the process of conversion require more catalyst. And we do have systems, corn oil refinement systems that will take the DCO and remove heavy metals, phosphorus, silica, things like that are inhibitors in those processes. I don't know, but perhaps those are some of the same elements that make it unsafe for human consumption. I would need to talk to regulators, as I said, to better understand that. But there are ways of taking raw DCO and increasing its value for the renewable fuels sector.
Okay. Thank you.
Yeah. If you reach out to Mr. Ramesh and give me your contact information, I'll certainly follow up with you with whatever I find.
Yeah, yeah, I will be. Thank you.
Right. Yeah.
Thank you, Kapoor sir. Thank you, Chris. And Chris, there are a couple of more questions in the chat box. You can go ahead with them also.
So how much DCO percentage production per ton of maize in a previous slide? If you go back, I give some estimates on that, depending on extraction efficiency based on low, nominal, and high performers in the industry or separation efficiencies. That that will fluctuate. Again, it's really important not to use just a stagnant number of this percent of oil in the incoming corn. Rather, it's much more beneficial to look at it from a separation efficiency, an extraction efficiency perspective, where you're doing an analysis on the feed and seeing how much free oil is available and then how much is removed. If you take that, how much free oil is available, we can influence that by some of the process conditions that we talked about today and several others. But a good rough estimate to start with is taking those worst case, middle case, and best case scenarios that were on that previous slide and applying it to your grind. Wax content. So I don't have that memorized, but Raul, I can certainly follow up with you with that. That is one of the things that we look at in the refinement process, and we can we can have a much deeper conversation about that. I may bring in some of our scientists as well to be able to talk a little more specific on that. But I'd love to have that conversation. That's something that that Trucent is well versed in. I just don't have that memorized, but can absolutely get you those numbers. Similar per how much corn oil per metric of ton. If you go back and refer to that previous slide, that'll give you a rough idea, a good starting point. And then if you reach out to Mr. Ramesh, we can do a case study for your particular plant. Give you a little more depth to the information, if you will. Oh, great questions. So how many discharges are required per hour? Is any oil lost in the discharge? How much water is needed per discharge? What are the parameters and analysis needed to carry out DCO for sustainability for biodiesel production? So I'll take these one by one. How many discharges per hour? So this is referring to the vertical distack and the solids discharges. So that's going to be dependent on the solids loading that's it in a per volume basis. So volume of solids by volume of liquid syrup. So solid versus liquid. Generally speaking, it's somewhere between, depending on the size of the centrifuge, a discharge every 3 to 5 minutes, 3 to 6 minutes, somewhere in that range. Is any oil lost in the discharge? I'd say yes, but not to that much of a meaningful impact. So the way that you discharge will affect this quite a bit. Now we're getting into the centrifuge design and some of the nerdy engineering stuff that I love. There are two basic types of solids discharge: a full discharge and a partial discharge. A full discharge is where you're expelling most of the volume of what is in the bowl, and if you do that, yes, you're going to have a larger amount of oil that is leaving the bowl. So the 3 to 4% of the volume that is lost in the bowl. So if you've got 2 gallons of oil in 2 gallons of syrup in the bowl, 3 to 4% of that. The way that we discharge is what's called a partial discharge. We have a operating water system that allows us to control the discharge to within about 0.2 of a second. So this discharge is very, very quick, and we're able to open and close the bowl in a way that we're only discharging a portion of the volume. We're targeting just the solids holding portion of the bowl or volume of the bowl. And by doing that, we have a more efficient discharge, but then also a more efficient fluid dynamics within the bowl during the recovery. So if you imagine these solids leaving, it's going to disrupt the fluid dynamics in the bowl temporarily. So you'll see this increase in volatility in the bowl, and then it'll settle out, and you'll get to a better separation. This is where some of the value of the corn oil conditioning system comes in. I would say it's much better to have a dirty cut of oil that you can clean up rather than have missed oil. Once you miss the oil at the centrifuge, it is going to be going to DDGs. But if you set the centrifuge up and the discharge is up, where when you have a discharge, instead of losing oil, you're just creating a dirty cut of oil coming out of the centrifuge, you can then condition that to still meet spec and to remove those impurities. And that's where the big value of our proprietary conditioning system comes in. So in not just the discharges, but the way that you set up the operating conditions of the centrifuge. So for vertical distacs, it's things like back pressures, flow rates, a few other variables. On the horizontals, it's going to be the weir position, which is what defines the inner and outer diameter of the two liquid phases. It is much better to have a dirty cut that you can clean up rather than miss the oil altogether. So a really good question that really goes to how you optimize a separation. How much water is needed per discharge? The way that vertical centrifuge discharges work are by there's a false bottom in the within the bowl, which in its upper position is blocking the discharge ports. In order to actuate that, what we're doing is operating a little bowl control valve, if you will. It takes a very, very small intermittent amount of water. On the larger machines, it's maybe a liter per discharge. So it's not a significant amount of water. What are the parameters needed to carry out the DCO for sustainable biodiesel production? So biodiesel, I'm going to answer this specifically for biodiesel, and which is the parameters are different for renewable diesel and renewable or sustainable aviation fuel. Biodiesel, where you're just adding a percentage into the existing diesel, are pretty loose. I am not a biodiesel expert. I'm a centrifuge expert, but we do have literature on that. I can follow up with you with that literature and with some of our team members that can speak more intelligently and freely on the biodiesel process and its parameters and demands. If you can give me your contact information, I can send you those papers and put you in contact with people that can talk in more depth. Oh, these are some great questions. Thank you guys for them. Where will this be installed? At what stage of the process? So the majority of systems in existence around the world are on what we call either mid-evap or on syrup. So in your evaporator train, we're going to do an analysis after each effect and find the most optimal concentration of solids and oil. And that's where we'll pull it off. What we have seen in India is that generally that's going to end up being on syrup, which is more and more common in North America and across the globe. It'll be after the last effect, either going to a holding tank or directly to the centrifuge. We'll do the oil extraction, and then your solids and de-oiled syrup phases, or your solids and heavy phase, are mixed back together and are sent downstream to the back end and dryers. Trucent does have recovery or efficiency guarantees. We guarantee over 90% free oil recovery. Many of our customers are 98, 99, 100% recovery, and our team is available and constantly working with our customers to do the analysis and work that is needed to get those higher end efficiencies. But our guarantee is 90% in our installation in Punjab. We without making any adjustments right off the bat, we were making oil that was 0.7 to 1.1 moisture and impurities without making any adjustments and recovering over that 90% threshold. So the system design, the auxiliaries around it, those are we say the devil's in the details. That's where you get those higher end efficiencies by taking spin samples, looking at what is coming in, if there's any oil left in the heavy phase as it leaves the centrifuge, the quality of the oil coming out. All of those will tell you, left one out, the samples before chemical dosing and after are very important as well. Those four main samples should be taken regularly, spun, looked at under a microscope to be able to really dial in the operating conditions to get those higher efficiencies. As you can imagine, the feed makeup may change from fermenter to fermenter, certainly from longer time periods and definitely from different harvests. So again, it's really important to look at what is available in the corn coming in, and then what free oil is available to the centrifuge. That free oil number, when you do those spins, if it is low or if you're seeing a high emulsion, then we start looking at what is causing that. So looking back at chemical dosing, looking back at heat history, what's going on in the evaporators, and that's where our experience really provides value. Temperature, required temperature. So the hotter the better. Generally speaking, there is great benefit as you increase to get to a point where you're at about 85, 90 degrees Celsius, and that tends to taper off. But that's not to say that we can't separate high quality oil down at 70, 75, 80 degrees Celsius. So from a engineering perspective, with my engineering hat on, the hotter the better, up to about 90 degrees, 95 degrees Celsius. Excuse me, 85, 90 degrees Celsius. But from a energy usage, availability, and business standpoint, we can help you find where that sweet spot is for your particular plant. We can do a case study, mass balance, all that. If you reach out to Mr. Umesh, we'll get your particulars, and we can put all that together for you so that we can work with you on the process, both upstream and at the extraction point, in order to optimize. What percentage free oil can be recovered? Great question. It all begins at the design and centrifuge selection point. That's where you obviously get your largest benefit. Starting with a centrifuge that's designed for this, there are, like I said, a lot of centrifuges out on the market. Make sure there's one that is designed appropriately for corn oil extraction is the first step. And then the process around it. So like I said, we guarantee greater than 90%. Most of our customers are over 95, and we're as high as full recovery of free oil. Rice is a feedstock. Man, I wish there was a discernible fat content in rice. There's no free oil in rice, which is the bad news. The good news, though, is unlike other grains, rice doesn't seem to affect corn oil separation. So the extraction efficiency, all the variables that contribute to that. So if you're running a blend of rice and corn, you can still get that oil. Now, obviously, the less corn that you have going into your mash bill, the lower your yield is going to be. But you can run that same calculation. So depending on what the blend ratio is going to be, you can do a calculation to see what your recovery is going to be, what your yield is going to be on a blend. But if you're running 100% rice, there's no free oil available. So the system can only separate what free oil is available. So there won't be anything coming out of the system. Ooh, what are the possible causes of low oil recovery? That's a big list. So looking at the corn coming in, seeing what is coming in the kernel, your enzyme dosing, your fermenter quality, heat history in distillation. A big area to look at is the decanters. When you're going from whole stillage and backset, the oil that's in the solids that are being extracted at the decanters is obviously going to be missed. So having a efficient running decanters efficiently is important. The amount of backset oil is in that. Now that's going around to the front end and is going to come back to us. But it is still not being directed to the corn oil extraction system, so that's going to be missed. The way the evaporators are performing, the tied to that is the viscosity. So what is happening in the evaporators? If you're concentrating the solids up and are creating a really viscous feed to the centrifuge, that will absolutely decrease oil recovery and cause other problems. And then everything around the centrifuge and the extraction itself, additives, temperatures, centrifuge design, the way that you set up the operating conditions of the centrifuge itself. All of those are contributing factors and more that I'm sure I'm missing off the top of my head. And that's where experience comes in, of being able to balance of the operating conditions and know where to look when. Again, I know I keep going back to sampling, but it is incredibly important. Running sampling and running lab tests. We provide lab SOPs, what to sample, how to treat it, what those tests are going to tell you, where they're going to tell you to look. And then our team, both in India and the rest of the world, are available to bring our experience to the table to help make recommendations. Does Trucent provide an entire turnkey solution or just a centrifuge? We provide the turnkey system. These are skidded units, so they land at your doorstep, ready to be installed and run. The program controls, the touchscreen interface, all of that is included. We bring all of our experience with it as well, but what we have, the automation that we have created in the program and controls is brings a lot of value right off the bat to be able to get high recovery, really efficient separation. So we try to make it as complete as possible. Does the system come with inbuilt product heater? No, it doesn't. The amount of heat needed is going to, or needed or wanted is going to fluctuate from customer to customer, from plant to plant, depending on size, flow rates, and many other operating conditions. So that is done on a case-by-case basis. We give recommendations, and our engineers work with each customer to create a full package to be unique for your conditions and your goals. All right. I think that's everything on the chat. If there are any other questions, please either put them in there or ask.
Thank you very much, Chris, and fellow participants, for making the session very interactful and informative. Thank you once again, Chris. And there is a small token of appreciation from GEMA for your quite knowledgeable session for the GEMA members and the industry fellow members. And is any other participant is having any other questions, so they can ask. Otherwise, we can conclude the session. Thank you.
Thank you all. I look forward to hearing from many of you.
Great,
Thank you.
Yeah, thanks, Chris. Thanks, Nitin.
Thank you.
Okay, Chris, then we can close the session. You two have a great day ahead. Thank you.
Great. Thank you for the opportunity. This was great.
Great. Thank you very much. My pleasure.
Thanks.